The circular number pi has fascinated mathematicians basically ever since, and many sophisticated algorithms have been developed to approximate it. For example, you could try to approximate the circumference of the circle by finer and finer regular polygons. But this is very tedious, especially if you're living in ancient Greece and you do not have a calculator. But what if I told you that you do not need to be a genius level Greek mathematician to approximate the value of pi? In fact, the only thing you need is a function that can spit out uniformly distributed random numbers in the interval 0 to 1. And you should be able to count, but that's all you need. If you're wondering how that can be possible at all, then stay tuned, we'll find out. And actually, we will also learn a little bit of probability theory on the way, which is, of course, always a good thing to do. And with that, welcome back to Probably Optimal. Nice that you're here, and without too much talk, let's dive right into. So the first thing that we need to realize is that since the random numbers are distributed uniformly over the interval 0, 1, for any subinterval from a to b, the probability that a number lands inside AB is exactly given by the length of the interval, that is by b minus a. But then, by the law of large numbers, this tells us that the fraction of points that will land inside the interval AB is approximately the same as the length of this interval. And while this is already quite nice and good to know, it alone is not sufficient to find pi. So the second thing to realize is that nobody really said that we can call the function rand only once to create a random point. In fact, if we simply call it in pairs of 2 and treat the first number x as x coordinate and the second as y coordinate, then we actually get a two-dimensional random point in the unit square. Then, if we do this, these two-dimensional points will be distributed uniformly in this unit square. So whenever we have a subset A, the probability that such a two-dimensional random point lands inside A is exactly given by the area of A. And by the same logic as before, this in turn tells us that the fraction of points that land inside A is approximately the same as the area of A. So, how does this help? For this, we can simply draw a quarter of a unit circle into our unit square. Then we know that the area of this quarter circle is given by pi divided by 4. So, according to our considerations from before, we know that we can approximate pi by 4 times the fraction of points that land inside this quarter circle. But wait, how do we actually know that one of our random points did land inside the circle? To figure this out, let's denote our random point by the tuple xy and recall the Pythagorean theorem. We know that the square root of x squared plus y squared is equal to the distance of our random point to the center of the circle. Therefore, if this distance is smaller than the radius, which is simply 1 here, the point does lie inside the circle, and otherwise it lies outside. So, given this condition, we can finally simply create many random points and just start counting. And if we do this, we can see that, in fact, our approximation gets closer and closer to pi, even if it's a bit slow, to be honest. And do you know what's also cool about this strategy? It actually also works if you consider the full circle, or even if you go to 3 dimensions and consider the sphere. In fact, using such a Monte Carlo technique, you could easily approximate the volume of the sphere. The only thing you have to do is to call your function rand 3 times for every point, and of course you have to adjust the formula slightly, but then you're already good to go. So that's it for the video. I hope you enjoyed it. I hope you could learn something from it, and thanks for watching.